Thanks, Bob. Thank you. All right, thanks, Bob. Thanks for having me back. I'm excited to be here tonight because we're going to be showing you some state-of-the-art technology and the implications it has for the way we do our geosciences. Before I get going, I do want to introduce, I should have introduced two guests here. Mike Conway back here is the head of our outreach program at the survey. And with him is Rory O'Rear, who's a student working with us part-time. And Rory's going to videotape this tonight because this afternoon we signed a contract with the U.S. Department of Energy for an $18 million geothermal data project. And so it was the second largest award given by the Department of Energy for geothermal in the United States. Out of $340 million, we got the second largest award. And so we're pretty excited about that, but part of the new program is that we want to get some videotape, some of our presentations together. So we'll have slideshows and poster sessions, but our outreach folks wanted to get at least one or two of the talks describing what we're doing and how it works. So Rory's going to videotape this, and we'll be putting this up on our website as we get the new project website fired up. Question was, is the funding in a secure site so the legislature can't get to it? It's about to be. We are modifying our budget process, actually. We met this morning on it, so that the indirect costs from this project will stay within the federal grants funding within the state. And within that, they cannot touch it by law. However, they still sent us a bill this morning for $88,000 saying, well, it's stimulus funding and therefore we want a piece of it to pay for the people that we've hired in our office to track stimulus funding, and you'll pay their salaries. So, so we've asked for a waiver from that, so we're already working on that one. But when I joined the survey a little over 4 years ago, one of the goals I set is that all of our data would be digital, all of it will be online, and all of it will be interoperable. Most people don't understand interoperability, and there's a lot of debate over it, so we're using the word data integration more, with the idea that we want digital data that you can bring from any software, any server, any computer system, and bring it to your desk and seamlessly integrate it. Right now, it's estimated we spend 75% or more of our time going out there and gathering data and converting it so you can get it in the same format. And you only spend a small portion of your time actually working with the data to analyze it and coming up with results. We want to cut that 75% down to 25% or 10% or less so that it all comes to you seamlessly and integrated, and you work with the data rather than spending your time trying to convert it. So what I want to talk about is tonight the efforts that we've been taking in the last few years and the tremendous acceptance of the approach we've taken in the last year. So I've got two parts to this. One, I'm going to do some PowerPoint slides, and when that's done, we're going to do a live fly-through, bringing in data from different computer servers around the country, live here in real time, and fly around and take a look at layering these data and starting to work with them to give you an idea of how this system is going to work and what it will bring to your desktop. So let's see. Page down, okay. So the web is only, 15 years old or something like that? But there's hundreds of millions of websites, and I use the number 200 million. Some people estimate it's many times that. But today, if you do not have a website as an organization, you do not exist. You are defined increasingly by your website. That's how people find you, they know you. Anything about you, it's on your website. If it's not there, you're invisible. The prediction I'm going to make is that within the next decade, scientific organizations, organizations dealing with data, are going to be invisible unless your data are online in an integrated, interoperable data system. If you don't do that, in another decade, you effectively will not exist in the modern world. So if you think about it, we have thousands and thousands of databases among us. This is from a meeting we had with the USGS and the Association of American State Geologists. the different kinds of databases out there. And at the time, USGS had just done an internal inventory and thought that they had at least 1,000 databases and many more that they hadn't counted up. But it's not just in geology and hydrology and geophysics, but think about the biological surveys that they have within the USGS and vegetation maps and things like that. So when you start bringing in the other domains, but the problem is none of those databases work with any other database. It's a Tower of Babel when you're trying to deal with digital data, or non-digital data, even worse. Today, if you're trying to bring data together, you're working with different varieties of software, different proprietary software that won't interact with other software. He's got different data structures within their databases, different names for things, for the same thing with different names. You cannot bring these things together. So it's very frustrating. Our goal is to seamlessly integrate all the data, regardless of operating system, servers, software, variety of softwares, and bring it to your desktop seamlessly. And the challenges are not so much technical. The technology really exists. When we go and talk to the IT community about this, they're going, well, wait a second, you can do this, you can do that. There's no cutting edge here. It's just you have to apply this or decide which version of this you're going to do or how you're going to do it. But there's nothing exciting for the IT world to say this is off the shelf to a large extent. The real challenges have been getting everybody to agree on how we do this. And for the past decade, a number of us have been fighting in the community to try to figure out how we're going to make this happen. And so think of it this way, and I've chosen the Death Star here very deliberately because the debates we've had in the community is who sets the standards on how this system is going to operate? Who controls the system? Who becomes the data czar in the geosciences? And who makes these decisions? That has been a huge fight, and there's been tremendous concern that somebody or some group ends up controlling everything. And early on, people were saying, if you're in charge, you're going to make me convert all of my data over into some other system. And I have to have my system and my software and my capabilities, and I don't have the time or money to convert it into something that you want. And so this idea early on of a central data system or a giant database and just send me your data and I'll put it in my database and I'll control it and I'll be in charge of it, nobody would buy into. There was modest success here and there in a few cases, but most people were terrified of giving up control of their data and having the dark force in charge of this data system. So what's happening is that there's been some changes in technology. It wasn't that many years ago that you're sitting there with your computer and you buy a new printer. Well, when you did that, you had to go and find a driver, a software driver that would link the software in that printer with your computer, and it had to be customized for it. And hopefully it came with the piece of equipment you bought or the software you bought. Or if it wasn't, you had to ask for them to send you a CD or a diskette, or you have to go online and look for that driver and find that driver. And there was a specific driver between each piece of software and each piece of hardware. And so it was a tremendously complicated system. The system today has changed. So what happens is we've developed some very simple common interchange formats, a meta file, that are standardized. So if I'm writing software, I don't have to write a driver for every piece of equipment that's out there. I write a driver that goes to this interchange format. And on the other side, if I have a piece of equipment, I write a driver that goes to the interchange format. And what that means is you only have to write one driver for each application or each piece of equipment. And you don't have to know anything about the equipment over there if you're building software. You don't have to know anything about the software if you're building the equipment. All you have to know is that there's a common interchange format, and if you write the standard to that, it all happens. That's the basic concept of where we're going. And we all use these common interchange formats today. If you go online, if you use the web, you're doing it every day. The interchange format is HTML, Hypertext Markup Language. It's a markup language that's an interchange format. So it takes images, documents, databases, video, anything that's being served via the web and converts it using this interchange format in a standard output so that anybody who builds a web browser or an online application, all you have to do is write the conversion to HTML. You don't have to know anything about the stuff coming here. So that's the basic concept of where we're going. So 3 years ago, we got together, the State Geological Surveys and the USGS, at a 2-day workshop in Denver, and we recognized that we had unique missions. Geological surveys are different than a lot of, say, universities or labs or government agencies, regulatory agencies. We had an obligation to collect data, to archive it, and disseminate it. Universities don't have that obligation. They're doing research. But once the project's over, there's nothing that says keep the data, store the data. In fact, there's a disincentive because that costs money. The project's over, you move on. The data disappears. Companies throwing data, throwing samples away. So we realized we had a unique mission. So we got together, we counted up, we said, you know, we think there's at least 2,000 or 3,000 databases among the 50 state surveys in the USGS. We had already counted well over 80,000 geologic maps and had a database linking all of those together. And so we came up with an agreement that we were going to build a geoscience information network to exchange the data among the geological surveys across the United States. And the concepts are, it would be a distributed network, not centralized, which means all the data resides at the source of the data. So every state geological survey holds on to their data. We hold on to ours. We choose what we make available to the network, just like we choose what we put on our websites. So we decide what data we're going to put out there, in what format, in what database, what servers. Web-based. So it's all going to be run through the internet. We're going to use the World Wide Web. Interoperable, this idea that we want the data to come from all these different sites. We'll use an interchange format to convert it on the fly so it's delivered to your desk seamlessly and integrated regardless of the source and the format. And open source, no proprietary software in building the system. Open source so you don't have problems about having to buy the software or the version's out of date. It's open source, it's community driven, but if you have proprietary software that you want to use with it, that's fine, but the operation is open source. One of the big things in selling this to everybody is nobody was telling you, you have to do it. Most of us have websites because we realize we have to have them out there. Nobody's coming and ordering us to build a website. We realize that's how people discover us. We're hoping that as we build this network, people will recognize the value of bringing all of these data sources together. And as the surveys bring thousands of databases to the web and put them out there, we're hoping other people will say, great, I'll use the same standards, the same protocols, and I'm going to share my data. And in doing so, I have access to all of those other resources, and people will start building applications to take advantage of them. So here's partners. In the last 2 years, we have got funding from the U.S. Geological Survey, National Science Foundation, a couple of grants now with the U.S. Department of Energy. We've got partnerships with major corporations across the country, and some small ones, some big ones, and we're building partnerships on the global level with a variety of the geoscience community that are working in data integration and data sharing. For example, Microsoft Research is a partner on this new project that got launched today. When we turned in the proposal back in July to the DOE for this funding, they released that day, made public, their new data integration web portal called SciScope, and that's Microsoft SciScope. And here's a comment from their launch of it. It's a tool to help geoscientists discover data from different data repositories through a single intuitive interface. You can bring all of these different things in, interact with different geography features and different types of data. They're serving up millions of data sets, as they describe it, from a variety of federal agencies already. They're going to make this an open source software, donate it to the system, and they're building that. So when Microsoft comes along and says, look, the data integration capabilities you're building are so important, so valuable, we will start building applications to take advantage of it. That's how the web worked. When the web was built, there was no Google or Yahoo or search engines or browsers. A bunch of geeks in dorm rooms said, wow, look at all the stuff that's coming across the internet through this web. Let's go ahead and build some things to take advantage of it. We're doing the same thing. If we build the data integration we expect people are going to come and they will bring new tools to the table for us, and we're seeing that happen. So the National Geothermal Data System is a separate project funded by the Department of Energy starting last May. We at the survey in Arizona are partners in that. We are using our Geoscience Information Network as the data integration mechanism to make this national data system work. And so if you're sitting there at your desktop and you decide, I need some information on this geothermal system, I'm going to go into the NGDS and see what I can find. So what does this system look like? There's portals. You can come in through Microsoft SciScope portal. There's a group up at Boise State that's using a portal that they had built for other purposes, and they're converting it over here. Anybody who wants to build a portal into the system, you're welcome to do it. We encourage it. It's open source. If you can build a better widget, build it. So you as a user decide how you want to go into the system. We're building network communications and controls to explain how this works, how the data moves, how the controls move back and forth. So you send a request up through the National Geothermal Data System. This project, it's a $5 million 5-year project. It's headquartered out of Boise State. We're a subcontractor on that to build the basic network communications and the discovery, access, and exchange mechanisms using our Geoscience Information Network on how we're going to work within this environment and bring the data together. Also, dictionaries, basically. Your granite may be somebody else's diorite. So how do we build these ontologies, these vocabularies, so that when you're asking for a granite and somebody's called it something else, you can figure out how to interpret that and bring those data back. Data models, how we structure this so that when people are putting data, making data available into the system, how you set this up to know what are the parameters that need to be included in there to really make this robust so we can find what's out there. Distributed sources. So here, among the 50 state geological surveys, USGS offices, universities, national labs, and others. But the signal, the request goes into the system, it goes out there and searches among all the nodes, all the repositories that have linked into the data network, said we are sharing data, we've published data, here's data that you can access through the network at our shop. It goes out there in these distributed sources, finds that information. Also, we will have a repository for legacy data. There's a lot of data that has no permanent home. So we're setting up some centralized databases that will preserve the data that's at risk of being lost, disappearing. There's a lot of data out there, and so part of the project will be to try to capture that data and make sure it has a permanent home. And we may see multiple repositories being set up. Anybody can set up a repository and make that available, link it into the network. We gather that stuff up, we feed it back to the desktop. There's the data brought together, and in this project, our friends at Boise State are building some desktop applications, one that's called Geothermal Desktop, specifically for this project, to provide some basic capabilities on your desktop to process and work with the data when it brings it back. There will be other proprietary software that you can buy off the shelf that will be able to work with this, and people will be building some customized things to take advantage of the vast quantities of data that we're going to be bringing. So the way this network is set up right now, Boise State is building NGDS. We have just come on now with this new $18 million project to deploy this network with a node in every state in the country, primarily through state geological surveys, and populate this network in every node with state-specific data. We will have terabytes of data being digitized or being linked into this network. We will have a server hub here, and then we're setting up 3 regional server hubs and training centers in Reno, in Champaign-Urbana, and in Lexington, Kentucky. And it will also link in with USGS offices around the country. So this is a little bit conceptual. One advantage of doing this is that the servers can scrape the data on a daily basis or something like that, because when you start moving gigabytes or terabytes of data and having to convert it on the fly, you can choke the system very quickly if you have vast quantities. So the thought is we can go in and scrape the data, archive it. That way if somebody's system is down, if somebody has electrical problems, if somebody goes out of business, we've archived it, we've backed it up, and we can also speed up the way the network works. Each of these regional hubs will also serve as a training center where we're going to be doing short courses and webinars and one-on-one training with emails and phone calls and traveling out. And so to help everybody get up to speed on how you can participate in the network. And early on, it'll be mainly for our partners in the project, but very quickly we will be developing online training materials and cookbooks and guidebooks and seminars that will allow anybody who wants to participate in the network to get up to speed very quickly. So just a quick example of some of the types of data that we've committed among the 46 states right now that are formal partners in this. But we're going to be going through at least 3.5 million wells, oil wells, water wells, geothermal wells. We expect we'll end up with data for at least 2.1 million wells. A couple of 100,000 well logs have been committed already by states, 50,000 specific geothermal wells, 3/4 million bottom hole temperatures. There's a decimal point missing. This should be 6 terabytes of digital data already there, we think is low-hanging fruit that can very easily be made available. 77,000 publications are going to be scanned, turned into PDFs, and made available. We've already done that here in Arizona. All 30 years worth of geothermal publications are all PDFs online and downloadable at free from the website. So we're going to be expanding that concept nationwide. So millions of feet of core with data coming in, hundreds of thousands of sample logs. It just goes on and on. This is just a partial list. It's probably going to be 2 or 3 times this when we start getting into the nitty-gritty. It's a complex system. Because of the 46 subcontractors and the complexity of what we're doing, DOE is funding this thing, but we've got a management advisory board we're setting up with the Association of American State Geologists because we're doing this on behalf of this group nationwide. Technical board that will work with us to make sure the technology we're using is appropriate and is going to be the best way to go forward. A science board that's going to set priorities on the type of data, the quality of data, the priorities of data that will be fed into the system. Now, as we're building this, we're not alone in the world. So we've been putting this together in the US, and we've got the geological surveys together, and other groups have come along and said, well, great. That looks like something we can use. We'd like to piggyback on that and take advantage of the network you're building. And so the National Geothermal Data System came to us, the people building that early on, and said, this looks like the mechanism we can use to build this system. So we're a partner on that, and now we've got this new money to deploy it and populate it nationwide. In Europe, there's a consortium of 21 countries and a half a dozen other organizations that are building a similar data network, comparable to ours. And we're working together to use the same standards, the same protocols to link the 2 continent-wide networks. There's an industry consortium in the petroleum industry called Intergistics that's focused on dealing with data standards in the petroleum industry. It's a nonprofit group to avoid restraint of trade concerns, so they've set this up. 97 of the world's largest oil companies and national oil ministries are members of this. They have signed on as a formal partner with us. And lastly on this slide, One Geology Europe is a spin-off of One Geology on a global sense, and I'll show you a slide on that, but 116 countries now are collaborating on sharing digital geologic maps online, live from servers around the world. I think I've got, yeah. So here's the Intergistics group. They've set up a working group, and their goal is end-to-end discovery, access, and exchange of the upstream petroleum industry. Upstream meaning exploration and development as opposed to the refining and marketing end of things. So they want to be able to get same kind of things we do, is discover where the data is, access it, and exchange the data, bring it together on your desktop in an interoperable format. They have adopted our data network and the NGDS as a pilot project, as the prototype for data integration in the world petroleum industry upstream. One Geology Europe, as I mentioned, 21 countries plus a number of other organizations. It's a European Union initiative under the INSPIRE directive to create geographic homogenization of data across the entire European continent. And their technical people are working with our technical people. We are using the same standards, the same interchange formats. Our people are going off to Europe 3 or 4 times a year. They're coming over here. We're working very closely to integrate these networks. And then I mentioned One Geology. 116 countries now are serving, well, have agreed to serve up their geologic maps live from their servers around the world. I think as of today, about 40 countries have the technical capability. They're serving geologic maps, and so here's just a snapshot of the portal with examples of some of the geologic maps being served up live from sources all over the world. So the goal is to get every nation up to the basics of putting at least a 1 to a million scale geologic map live from their servers onto the web. And then the next step that we're looking at in the next year or so is move them into the interoperability data integration system. So where we stand right now is that very quickly the geosciences are moving towards an integrated approach for data exchange on a global scale. We are ahead of any of the other domain sciences. The other groups are turning to us and looking to us for guidance. The things we're doing are not being done anywhere else in the world from what we can see, but it's moving very, very quickly. And so you can see with these partnerships and what we're doing, I never mentioned what's happening in Australia. There's a huge program called AuScope, AU for Australia, but AU for gold, to try to integrate all of the gold, or I'm sorry, the mining and mineral related information in Australia in a similar system. And we've been working with their technical people for a decade in developing some of these standards and protocols. So with that, I'd like to close this down and move now and give you a live demo of what these capabilities are going to be like. So, okay. All right. All right. So we are using software from ESRI. ESRI is the world's largest manufacturer of GIS software. It's a private corporation, but most government agencies are using ESRI, and they have a new software product called ArcGIS Explorer. We're using the latest version of this that came out just this past year. It's still very much experimental in many ways, and so we may have some glitches, but this is free software. It's kind of like Google Earth or Bing or Microsoft's Virtual Earth used to be called. So Bob, let's hit it again, and we're going to zoom in and take a tour. This is a new data set that we are serving live. This is not a canned presentation in the way you might normally think. We are serving up this image of the Earth live out of ESRI's headquarters in Southern California. It's coming in over the internet. I've got a wireless connection right there. The data I'm showing now are heat flow data gathered by SMU and our partners up at the Great Basin Geothermal Center. This data set is being served live from down the street at the Arizona Geological Survey server. So this is a live feed coming in through a web service of these data. Next one. So I'm going to go in and take a little subset of these data. Here's the bottom hole temperatures. There were about 15,000 data points in there. These are, out of those 15,000, these are the samples, the data points that have bottom hole temperatures calculated in them. Again, another data set being served up live out of our server in real time. Next.
And those are color-coded by temperature?
They are color-coded by temperatures. I didn't put that on here just because it's real easy to crash this system because we're pushing the envelope here on what this was designed to do. Okay? Well, what I'd like to do now is some of the examples we're putting together. We're starting with Arizona. As one of the advantages of being the PIs on this project is we can develop all these capabilities here in Arizona and bring them to you, bring them to the state with this federal money coming in and all the support we're getting around here. So this is the state geologic map, 1 to a million. We're serving this live from our server down the street. Next. And we're going to go in and take a look at some of the different data sets. Here's thermal springs from Claudia's study, I believe. Claudia, you may recognize this. I think this was from your 1982 report. Yeah, we went in and digitized those. And also here in the tan are geothermal prospect areas, areas of greater geothermal potential. Next. And thermal wells, any well that had some kind of a thermal indication that it was above background. Next. So most of you may not be aware, but there's a variety of geothermal energy uses in the state, one of which out by Gila Bend, desert sweet shrimp. And so we've zoomed in now and we'll take a look at the, out here at the green. Let's see, Bob, is this the pointer? Yeah, okay. So let's take a look. So we're serving this up live. Here's some of these geothermal areas. Here's some of the springs showing up. And the next one of the things we can do with this is just superimpose a picture. So we're doing this live flyover. We can stop and zoom around, but in this case, we just pre-programmed this to go to various stops and then automatically grab these data live from the servers around the country. So there's just a picture we've superimposed, but they're using a geothermal waters to grow shrimp out here. You can go out and have a meal at their restaurant or buy the shrimp and bring it home. And boy, if you could invest today with the Gulf Coast shutting down for shrimping, this might be the place to put your money right now. Oh, Bob, next, I'm sorry. Yeah. Okay, so we're going to pull out next. Yeah. So we'll pull out, and I think from here we're going to take a look again, bring up the geologic map, but the next slide was, let's go in and take a look at the Rosemont copper project down here south of Tucson in the Santa Ritas. So we're zooming in here with our 1 to a million geologic map. We've kind of just pulled that off here, looking at the topography, looking with Tucson towards the north here, but here's the Santa Ritas. Next slide. Okay, so there's the 1 to a million scale geologic map, and you can see when you start getting down this detailed, it really starts washing out a little bit. So next slide, or next image. And this one may take a couple seconds to load here. Okay, so we pulled the geologic map off. Here is the proposed Rosemont copper pit, the tailings and the waste rock. Did I get that right, Jeff? Okay, all right, so just outline showing where that's going to be. Next, Bob. So then we have just completed in the last couple of months very detailed mapping, 1 to 24,000 scale of the quadrangles here. So we've shared that with the Forest Service, but here now live again from our server down the street, we're bringing in the detailed geologic map, and the way this will be set up, and you can do it right now if you go to our website and start zooming in on the state, you're looking at 1 to a million, and as you get more detailed or closer in, higher resolution, you automatically go to 1 to 100,000. As you get closer, you go to 1 to 24,000. And so wherever we have those maps, as we're putting them up, you will just get higher and higher resolution as you move in and zoom in on the map. So
acting like a series of overlays
you can treat it that way.
from different data sets that are on the state
Yes.
survey server.
Right now, most of these, we are serving them up live from our server. The way this system is going to work, and what we're starting to do, is that anybody else who wants to plug into the network can serve up their data layers, and you can come in and grab those and bring them in from multiple sources. So effectively, we're doing that. With the background image, we bring it in live from Southern California. We're laying here the geologic map. It's a service that we're providing, a web service on our website that we provide, and we bring it in. And so we have a variety of services, and you can choose data from those services. So the first service you saw up here was a service providing national heat flow data. And now we're serving up Arizona geologic data, and we have multiple layers. You can stack layers. Within the software, you have the ability to turn on transparencies. So you could have a whole series of layers and just change transparencies and look down. What we're doing, just because it was complicating things a little bit, is that we're removing a layer and putting another layer on. So there's some fairly abrupt transitions here. Bob, let's do.
Software match scales. How are you matching the scales?
The services are set up so that they're geo-referenced. And you'll see a couple of examples of some more specific things where that becomes more obvious. So Bob, next. So we pulled out here, and you can see it layered over the topography. And on this, okay. Some of these services are a little bit slow. There's big files moving. Okay, let's do the next one. Okay, in this case, we're going to strip the geologic map off now. And here's the land ownership map. So we could be serving both of those up at once and just moving the transparency so you could see one through the other. In this case, just to keep this thing moving better, we've just turned off a layer, turned on another.
What's controlling the business? If you tilt it, all the data sets tilt
Yes.
conveniently.
Right.
Is that done within what the
That's built into the software. So this is GIS software. We're pushing it to the limit beyond things that they had planned. So there's still a few little bumps that we're working out, learning how to make this work. But generally, once we take the data layer and we georeference it, or we, say, okay, this data layer here comes with this GIS shapefile, it has the coordinates built into it so that they all just stack. And you state which reference system you're using on it, which coordinate system.
And you're showing this with a standard laptop?
Standard laptop. Now this is a newer one, and it's got a little bigger RAM and a little faster memory on it, because this thing right now is a memory hog. Okay, when I was doing it with my little laptop, it would sit here and churn, and sometimes you'll see down here, it'll say streaming down here, and it's just trying to pull in vast amounts of data. They're working on a new version of the software that was supposed to be out here any day now, where they're going to provide more of this back at their supercomputer and put a smaller version out that's going to be much more nimble, and that you'll actually be able to save it. Right now, you cannot save this presentation. What we save are a set of instructions to say, go from this point to that point, and then bring these data layers in. But you can't actually save this presentation. So I can't take this and make a URL to it that you can go and watch it. This is live, and right now, this is the only way you can do it. Bob, let's go on to the next one. So we'll strip off, we're going to strip off the land use layer, land management layer. We're still in the same area. Here's Tucson, but now I want to show you just an example of some of the other things we're doing. This past year, we completed, let's do the next one. We completed mapping along 225 miles of the San Pedro River and its tributaries on a project for the Department of Water Resources that's going through adjudication of water rights. And so they needed to know where the river quaternary river alluvium deposits were, shown in green here, and to separate those out from other types of deposits to determine whether these were subflow of the river or groundwater. And so there's statewide adjudication of our water rights going on through all of this. And so we're now mapping the Verde River the same way, and this is being used by the courts then to decide who owns the water and who's responsible for things. So again, just showing you, I'm sorry, I keep trying to push this one, Bob, next one. So just a couple shots along here to give you an idea that this, we think, is a very valuable tool, especially for people who aren't used to working with maps, to be able to put this in 3 dimension, to be able to move around. At any point, we could stop and just start flying around, look at different angles, and increase the vertical exaggeration, swing around. Next one. So since we're over in this area, I think, okay, the next shot, we're looking south there towards Mexico. The next one, since we're close to Tucson, we're going to pop over there. Okay, Bob. Yeah. And here, you can get seasick here flying around on this thing sometimes. So what we've done on longer versions is we have a couple of stops along the way, so you don't kind of go up and spin around and come back down. We stage it a little better. But 2 years ago, or 2006, we had the heavy floods. Pima County was concerned about the debris flows that came down, so they worked with us, and we went out and mapped prehistorical debris flows through here to see if they might be a problem. And as you can see, a lot of the building went on before they recognized that there were debris flows, and people have built on top of debris flows and debris flow paths and channels. But fortunately, most of these are probably a couple thousand years old, and they appear to be very rare events. Not the 100-year flood, but the 1,000 or 2,000-year flood before you're going to see these repeated. So we're going to move on north across the state and stop in. Next one, Bob.
As a point of information, my house is on that image.
Probably under one of those, big green patches. Yeah. So we're moving northwest along Interstate 10. This is the Picacho Basin, looking to the north. Next slide, or next shot. So we're going to turn around and take a look. We've been working identifying earth fissures and mapping them in fairly high precision. This is the longest earth fissure system in the state. It's the Picacho Fissure here, crossing I-10. It continues for about 8 miles up, crosses the Central Arizona Project Canal. The different colors represent different certainties of the locations or continuity versus discontinuity in here. And so we now have all of the fissures in Pima County, or I'm sorry, in Maricopa completed, almost all of them in Pinal, all in Pima, and we're working over in Cochise. And within another year, we should have most of the fissures, known fissures, identified and available like this through our Earth Fissure Viewer that you can come on and get this down to looking and seeing if you have a fissure under your house. So next. I think from here, we're going to swing north, go up into the Phoenix Basin. We're looking at South Mountain here. And in this case, the dots you see here are abandoned mines. The state mine inspector has a database of about 10,000 abandoned mines, was complaining that he needed to set up some kind of a digital capability to view these things, but didn't have the resources to do it. We got hold of the database, and 45 minutes later, we were projecting them on the map. And the biggest problem we found was there were a few hundred of them that had key punch errors, that numbers were transposed or plus signs instead of minus signs. So there's a few hundred of them that end up outside the state. So we're working with them to clean up that database. So, and one of the things we can do, Bob, if you could take the mouse and just bring it over, can you run the mouse over, say, this one, and left click the mouse on that button, and just hold it, yeah, just for a second there. Oop. Okay. No, you're moving the you're moving the image.
Sorry.
So, okay. Okay, there we go. All right. There's the data set that comes with that point. So the way the system works up is, yeah, we're working mainly with maps, but with data points on it. And here's some of the background materials. So you can make these layers, you can put an infinite number of layers of additional data about any data point into this system and be able to scroll through that and bring up these additional data and then be able to process the data that comes up with it. So in this case, there was no name in the database, and this is the information that was available through the state mine inspector's database for that point. So okay, so Bob, if you'd go back up, and I think if we just, go forward here, that should close that. Now we're just going to reorient ourselves. There's Sky Harbor Airport. We're looking northwest across the Phoenix Basin. Just to put you in perspective, in the next shot, we're going to move to the northeast out over the Holbrook Basin, where we've been doing some work on the potash deposits out there. And about a year and a half ago, we released the first inventory resource assessment of the potash resources out here. This is Steve Rousey's map from 0 to 10 feet isopac thickness to 20, 30, and 40. And so he's calculated that we have somewhere between 600 million to 2.2 billion tons of potash in place, depending on the quality, the percentage of it sitting on top of the salt bodies out there. Bob, let's go to the next one. And so now we can take this and we will just put the contours up there, but then show you the land ownership underneath the contours. And if you notice this big block right here, that's Petrified Forest National Park. The thickest part of the deposit lies under the national park. The rest of this are state trust lands and then the old railroad checkerboard lands through here. So it's state trust and private lands dominantly, other than the national park here.
Can you print screen on any of these images?
I would think you could. Yeah, I don't see any reason why you couldn't. Yeah, and actually in the presentation, the way this is set up is this is treated as kind of like a snapshot. So when I go in to edit this, I've actually preserved this as a slide in the presentation.
So you can PDF or JPEG this thing of this stuff?
We haven't tried doing that, but we probably could. Yeah, it would seem like we ought to be able to do that.
Save any of these images to
Right. Yep. Okay.
As soon as you do that, what kind of, with the standards and stuff, what kind of copyright protections have you built in?
We have. The question was, what kind of copyright protections have we built in? Right now, we haven't built it in because everything we're serving is public. But we expect that some participants in this will have materials that will be copyrighted. And so when you try to grab that service and bring it in, it's going to come back and tell you, here's the restriction. Either you have to have a subscription to it or you have some kind of arrangement. But it's like on the web right now. If you go on, you can log on to all kinds of free sites, but there's a lot of things that are subscription. And you go in there and you try to bring it up and it says, great, sign in here, log in here, show that you're a member and do that. So the system is going to work very much like the web works, but data-based.
But I'm worried about the reverse. What keeps somebody from grabbing this image,
Yeah.
sticking it in their paper,
Oh, yeah.
copyright that, and claiming they've got the copyright on this data? Do you have something that always shows
Oh.
ESRI logo or?
Well, that's for the software, but they could do that right now. I mean, we're serving up gigabytes of data on our website, and
I wondered if you can embed something that says this was stolen from
oh,
someone source.
right. That's a key point, because early on, people were very concerned about the idea that if I make my data available, somebody's going to grab it and write the paper on it. They're going to pass it off as their own. They're going to alter it. So one of the conditions that we've built into this, now I shouldn't say conditions, but attributes that we've built into this, or are building into the system, is that when the data come in, when you make data available to the network, you expose it to the network, you publish it to the network, it will identify who the provenance, who the owner, who the source of the data is, and we want that built into it. And so that if I'm a data provider and I put it out there, I know how often it's being used, or maybe where it's being used, so I can get credit for it. Saying, hey, that data set we put out is being used by 700 companies, 52 universities, and 1,000 researchers. I can go back to the people who may be funding me to say that's how valuable this is or where we're going. If I'm a data user, if I'm sitting here and I say, okay, this is great, do I trust these contours? Who drew these contours? Was this the Arizona Geological Survey, or was this a freshman class in geology at a high school that did this as a little project? So I want to be able to look at that, and when I bring tons of data in here, to be able to say, okay, identify the data with different icons as to depending on where the source is. So if I'm looking at data and I've got a spreadsheet here and I'm saying, boy, there's a lot of funny data over there, I can say, show the ownership of the data. And it's like, oh, all of that data came from this one place. I may want to flag that. Or I look at it and they say it's not out of a peer-reviewed journal, or it's not out of a trusted source. And then I can flag that, identify it, and say, let me look at that in a different way. So that's a core aspect of what we're trying to build into the system. Bob, let's go on. So let's, the land map will kind of fade out here as we head north along northwest out to the Grand Canyon. This is a map published in 1989 by the U.S. Geological Survey. We scanned it. We just laid it down and just took a picture of it. Then we came in and georeferenced the corners. And so that's a paper map that we took a picture of and we've laid on the topography. Next one. So as we zoom in on this, you can see that even with just a paper map like that, you can still see it draped over the topography and give more of the three-dimensional image of it. The black dots are breccia pipes, uranium breccia pipes from the USGS 1989 map. And so Helen Ireland on our staff looked at that and said, oh, and within an hour she digitized all of those. So Bob, let's hit the next button. And she just put points up there, digitized them all. Breccia pipes, the ones in orange there, are the ones shown as mineralized pipes from the USGS report. So, next. Now I think as we move over here, we're probably going to pull this map off. Yes. And here's the 1,000,000 acres that the Secretary of Interior has pulled aside from mineral entry for a 2-year EIS process that's going on right now, with the idea of evaluating where this may be a 20-year or longer moratorium to mineral entry. And next one. Whoops. Oh. Okay. That's a surprise. Oh, you went backwards, Bob.
Yes, I did.
Right.
I wasn't looking at the computer
Yeah.
screen.
Okay. All right, so that one, so let's do one more now. And so we've just brought up, here's Denison's 3 mines. And Jim, you may be able to help me. Which one of these is the Arizona number 1?
I think it's the one on the left.
On the left.
That is the one to the right. That's
Okay.
Yeah, I'm right here.
Oh, okay, sorry.
Answering those questions since that's my map that all that's based on.
Right, okay.
And now I have to make a comment. One of the things environmental misleading. They said, oh, well, the land that's being withdrawn is only 11% of the land. I mean, doesn't it look like, look at all those pressure pipes available for the mining industry. They're only
Right.
withdrawing a little bit of land. The fact of the matter is almost all the rest of the pressure pipes are on parkland, Indian land. It's not available land.
Yeah.
What they're taking away is about 95%
Yeah.
of the real estate.
Yeah, and I could go in there and click and bring on the land ownership map and bring that up.
Yeah.
Here is another layer on top of this.
Not available.
Right.
So
Okay.
unfortunately, this is really misleading. If someone just looks at it, and that's where the environmental groups are
Okay.
all saying this.
Okay.
I mean, I'm not saying you're not.
Right.
It's just the fact of the way it
Yes.
comes out looking like that.
That it can be presented in a way to mislead
So
people.
they're
Yes.
basically trying to turn everything into a national park.
Yeah, exactly. I mean, they're withdrawing
And
everything.
they're doing the same thing in Utah, by the way. It's a 90 million acre thing going on.
Yeah,
It's
I
just
know.
northwestern.
Okay.
Fine.
All right. And Bob, I think there's one more, if you click one more time here. Oh, yeah. And then again, we just, we brought up just all the abandoned mines there as well, and you can click on those, and some of them have some more specific information. And so now, okay, let's go ahead and do it one more time, and this will,
The abandoned mines, you gotta know more than just the coordinates. I mean, are they does it tell you there's shafts or an adit or?
well, we showed you on the, on that one that we brought up, the example, that's all that was in the database from the mine inspector's office.
So they just knew there was something there, but it hadn't been really.
Well, it depends. They may have more records somewhere else, but it wasn't in this database. So they may have another database that goes into more detail like that. We'd have to get that and link that one to this. So what we're talking with them about is that give this back to them. They can serve it out, and we could link it into this network. However, after they started working with this, they got concerned over the potential liabilities. And so they're trying to evaluate what happens when they put this out, and people can put this on the ESRI product or on Google Earth and just bring it up and say, I want to go out and bring the Boy Scout troop to explore some old mines this weekend. And let's put it on Google Earth, and hey, there it shows me exactly where I'm going, and all of a sudden they've got some problems. So they're doing an internal discussion right now about how much of this they want to make public in what format. The database is public.
And I did the same with archaeology.
Same thing with some of the, sites that you want to try to preserve. So they're struggling with that, of how they're going to deal with it. So this is for our demonstration purposes. The abandoned mine database in a digital format or in a display format is not publicly available yet. So we've just stripped all of that off, put the 1 to 1 million geologic scale map on, and Bob, I think this next one will pull us back and bring us back to where we started. And so I think you can see that some of the capabilities that we're bringing together here are going to be very exciting. We showed you just a few services and a few data sets that we have up online right now that are available that you can do this with. And we're going to be adding thousands and thousands of data sets, tens of thousands of maps over the next 3 years from across the country. So it's going to be very, very exciting. And then as we start linking with our other industry partners and other government agencies, I think we're going to be seeing this become a tremendous tool for the geosciences. So thank you very much, and I'll be happy to take questions.